In this next set of exercises, we're asked to solve each single variable equation, which remember what that means. That means we're going to find value or values of the variable that make the sentence true or the equation true. So lots of different techniques to use. In 73, let's start by distributing the multiplication over the addition. That will give us 3k cubed plus 7k squared is equal to 6k. Now, since this is a polynomial equation, let's move all terms to the same side and try to factor. So we're going to subtract 6k, and then we're going to factor out k. And k times 3k squared plus 7k minus 6 equals 0. And then we need to factor a little bit further. I'm going to use a box to factor in. So I'm just going to do this off to the side. You can do the same by splitting the middle term and factor by grouping, but this is essentially the same thing. I'm going to put my first term and my last term of the trinomial in those boxes upper left and lower right, and then multiply a times c. A times c is 3 times negative 6 is negative 18, and we're looking for the factors of negative 18 that add up to positive 7. So those would be 9. So I'm splitting the middle term into 9k and negative 2k. Now let's grab the greatest common factor from each column and each row. From the top column, the greatest common factor is k, and from the right column, the factor is 3. And the top row, 3k, and bottom row, minus 2. So that means that our two factors are k plus 3 and 3k minus 2. Now, if the product of factors is equal to 0, then all the factors can be set equal to 0 in order to find the solutions. So k equals 0 or k plus 3 equals 0 or 3k minus 2 is equal to 0. That's going to give us three solutions, 0, negative 3, and positive 2/3. It doesn't matter the order in which you give these solutions. In 74, we have a quadratic equation, and we can bring the 1 to the left side by subtraction. However, when we try to factor using the AC method, the method for factoring a trinomial, a times c is negative 1, and there are no factors that add to negative 8. In that case, we need to try another technique that applies to quadratic equations. And so instead of moving that 1 to the left side of the equation, I'm going to leave it where it is and put a plus blank on both sides. I'm going to make a box for complete the square and put the first term y squared in the upper left, and then the negative 8y, the middle term, is going to be comprised of the two diagonal boxes in this literal square. And so I'm going to split it evenly and put negative 4y in each of those boxes. Now we can factor, and the factors will be y minus 4 and y minus 4, which means the literal completion of this square is going to be 16. So I'm going to add 16 to both sides of the equation, replacing my blank with that. And then the y squared minus 8y plus 16 is y minus 4 times y minus 4, which is the same as y minus 4 squared. And y minus 4 squared is equal to 17. And now we can solve by taking a square root. And when we take a square root to solve an equation, we have two solutions, plus or minus the square root of 17. Adding 4 to both sides, we have 4 plus or minus the square root of 17. So those are our two solutions. One solution is 4 plus the square root of 17, and the other solution 4 minus the square root of 17. In number 75, we need to clear the fractions by multiplying both sides by a minus 4. But before I begin, I'm going to note that a minus 4 can't equal 0. And if a minus 4 can't equal 0, then a can't equal 4. Just going to bear that in mind just in case we get an extraneous solution. All right, so we're going to multiply this first fraction by a minus 4. In doing so, we get a squared minus 6. I'm going to multiply this term by a minus 4. In doing so, we get 3a minus 12. And the last term, the fraction multiplied by a minus 4, is 10. And so combining like terms, we have a squared minus 6 is equal to 3a minus 2. And now I'm going to subtract 3a and add 2 so that all my terms are on one side. Then we can factor, and since the lead term is 1a squared, then we can use our shortcut for factoring. Factors of -4 that add to -3 are -4 and +1, so our factors are a minus 4 and a plus 1. And so if a minus 4 is equal to 0, then a is equal to 4. And if a plus 1 is equal to 0, then a is equal to -1. However, we know that a can't equal 4. Remember from the original restriction on the equation, so that's an extraneous solution, and the only solution to this equation is a is equal to -1. In number 76, we have a square root equation for which there is potential for an extraneous solution. So we just need to be aware of that so that we check all of the solutions that we get. So first I'm going to isolate the square root by subtracting x. And now we can square both sides. Squaring a square root, it just reveals the contents of the square root, 3x plus 1. And then squaring 1 minus x is 1 minus x times 1 minus x. We do not distribute squaring over subtraction. So I'm just going to multiply 1 minus x times 1 minus x, and we get x squared minus 2x plus 1. And now I'm going to bring all my terms to the right side where the x squared has a positive coefficient. So I'm going to subtract 3x. And if I subtract 1, the constant terms are gone. Now we're going to solve by factoring. And setting the factors equal to 0, x equals 0, or x equals 5, we're going to check those solutions. And when we check 0, 3 times 0 plus 1 under the square root plus the x value of 0 should equal 1, and 3 times 0 plus 1 is 1, so the square root of 1 plus 0 is equal to 1. That's a true statement, so 0 is a valid solution. Now let's check 5. Under the square root, 3 times 5 plus 1 plus the x value of 5 should equal 1, and that gives me the square root of 16 plus 5 is equal to 1. That's not a true statement, so x equals 5 is an extraneous solution, and we have only one valid solution, x equals 0. In number 77, we have a complex equation in which c plus 7 occurs twice. Whenever you see something like that, I want you to be thinking about u substitution. So let's let u equal c plus 7. In that case, 2 times c plus 7 squared becomes 2u squared. 5 times c plus 7 becomes 5u, and that equals 12. And now we have a quadratic equation. I'm going to subtract 12 so that we have a 0 on one side, and now factor. First term 2u squared, upper left box, and last term, constant term, -12 in the lower right box. And 2 times -12 is -24. Factors of -24 that add to -5 are -8 and 3. So I'm splitting that middle term using those two numbers as coefficients. So -8u and +3u, doesn't matter which box those go into. The top row has a greatest common factor of u, the bottom a greatest common factor of -4, and the left column has a greatest common factor of 2u, and the right a greatest common factor of 3. So our two factors are u minus 4 and 2u plus 3. If we set each of those to 0, we're going to get u is equal to 4 or u is equal to -3/2. And now we need to remember to back substitute so that we can solve for c. If c plus 7 is equal to 4, c is equal to -3. And for the equation on the right, I'm going to multiply through by 2 first. So 2c plus 14 is equal to -3. And that's going to give us a c value of -17/2. Both of these are valid solutions because I don't have the type of equation that produces extraneous solutions. Those are pretty much going to be limited to your square root equations and your rational equations, those with fraction with variables in the denominators. and also logarithmic equations. In number 78, we have a quadratic equation, so I am going to subtract 5m so that we have all of our terms on one side. And what I'm going to note here is that this is going to be unfactorable. 2 times -1 is -2, and I cannot find factors that add to -5. So since this is not a good candidate for complete the square, I'm going to use the quadratic formula. So m is equal to the opposite of b plus or minus the square root of b squared, which will be 25, minus 4 times a, which is 2, times c, which is -1, all over 2 times a, which is 2. So let's work on simplifying that. We've got to simplify that radical first, and then inside the radical we have 25 plus 8 when we find that product. Be careful with the signs there. So 25 plus 8 is 33. And then downstairs we have 4. Since the radical doesn't simplify and there are no common factors to cancel or to reduce this by, we've got that as our final solution. So we have two solutions, 5 plus the square root of 33 over 4 and 5 minus the square root of 33 over 4. In number 79, we have a fourth root equation. We can undo a fourth root by raising both sides to the fourth power, and that will undo the root. And 3 to the fourth power is 81, so 8w is equal to 80, and w is equal to 10. We can double check that result. If we double check that result, 8 times 10 plus 1 is 81, and the fourth root of 81 is 3. Check. In number 80, we have something in the form a square is equal to 25. Well, if something squared is equal to 25, that something that's being squared, which is the 1/3 b plus 2, could be 5, the square root of 25, right? So we solve by taking the square root. However, there are two solutions. That thing inside the squaring could also be -5. Now I have two simple linear equations to solve, but they do have fractional coefficients, so I'm going to multiply through by 3 first. 1/3 b times 3 is b, 2 times 3 is 6, and 5 times 3 is 15, and subtracting that gives me a b value of 9. And I'll do the same for my second equation. Multiply through by 3, and we get b plus 6 is -15. And if I subtract 6 there, I'm going to get b is equal to -21. And you can put that in solution set form if you wish. In number 81, I might first try to factor, but I'm now looking for factors of 13 that add up to -6, and that's not possible. So I think what I'm going to do here is use the complete the square method, since a is 1, the coefficient of n squared, and b, -6, is an even number, which means it's divisible by 2. And so n minus 6n plus blank is equal to, and we're moving the 13 to the right side of the equation, so it becomes -13 and plus blank. I'm going to draw a picture for my complete the square. I'm going to place the first term n squared in the upper left blank, and the -6n I'm going to divide into two equal pieces, -3n and -3n. That suggests factors of n minus 3 and n minus 3, making the literal completion of this square +9. And so n minus 3 squared is equal to -13 plus 9, which is -4. And now if I take the square root on both sides, n minus 3 is either equal to the positive square root of -4 or the negative square root of -4. So square root of -4 is an imaginary number 2i. So n minus 3 is equal to plus or minus 2i. Adding 3 to both sides, n is 3 plus or minus 2i, which means we have two solutions. One is 3 plus 2i, and the other 3 minus 2i. In 82, x over x minus 1 minus 3 over x plus 2 is equal to 9 over x squared plus x minus 2. This factors into x plus 2 times x minus 1. So I'm going to multiply both sides of the equation by that expression. So first term is x divided by x minus 1, which I'm going to multiply by that LCD. And then second term, 3 over x plus 2, also multiplied by that LCD. and that equals 9 over x plus 2 times x minus 1, also multiplied by that LCD. Now for each of the multiplications we can divide out the common factors, and that will leave us with x times x plus 2, which is x squared plus 2x, and then negative 3 times x minus 1, which is negative 3x plus 3. Don't forget to distribute the negative as well as the 3. And then on the right side we just have 9. So x squared minus x, combining those two like terms together, and now subtracting 9 from both sides, we have minus 6. This is an a equal to 1 factoring, so we're just looking for factors of negative 6 that add to negative 1, and those are negative 3 and positive 2. So x minus 3 times x plus 2 is equal to 0, which if we set each factor equal to 0 is going to give us x equals 3 or x equals negative 2. Now we do have to be careful about extraneous solutions. We need to be careful about the idea that either of those solutions may make a denominator equal to 0 in the original equation, which will mean some of the expressions will be undefined. And since a denominator is x plus 2, x cannot be negative 2, because if x is negative 2, then that denominator will be negative 2 plus 2, which equals 0. X equals 3 is okay, because it doesn't make any of those denominators equal to 0, so that's our only acceptable solution. In number 83, we actually have something here that's factorable. Y to the 4th plus 8y squared minus 9 is factorable, and so let's try factoring that one in a box. Put y to the 4th in the upper left and negative 9 in the lower right. So a times c is negative 9, which means we have a times c is negative 9, and factors of negative 9 that add to 8 are positive 9 and negative 1. So I'm going to use those as coefficients of the middle term, which is a y squared term. And now factor GCFs from each column and each row. So two factors are y squared plus 9 and y squared minus 1. So we can set each of these to 0. And if y squared plus 9 is equal to 0, then y squared is equal to negative 9. Remember, there are two solutions here since this is a quadratic equation. So if we take a square root on both sides, we're going to get a plus or minus type of a solution. The square root of negative 9 is 3i. And then we can do the same for the equation on the right. Add 1. Y squared is equal to 1. And so y is equal to the positive or negative square root of 1, which don't forget to simplify that. That's 1. So we have four solutions: positive 3i, negative 3i, positive 1, and negative 1. In number 84, I'm going to begin by distributing the multiplication over the addition in the parentheses. And then from here, we can add 3 to both sides. And I might try to factor here, but the problem with this is there are no factors of positive 3 that add to positive 2. And so in that case, I can use maybe the complete the square method, which means I'm probably just going to go back to my original step where the constant was on the right side of the equation and just place plus blanks on both sides. Let's make our picture for complete the square. K squared, and then divide the middle term into two equal pieces. Each is 1k, and so that suggests factors of k plus 1 and k plus 1, making the literal completion of the square 1 times 1, which is 1. So k plus 1 squared is equal to negative 2. That means that k plus 1 is the positive or negative square root of negative 2, which is I times the square root of 2. And adding negative 1 to both sides, negative 1 plus or minus I times the square root of 2 are our two solutions.